Hello friends, welcome to Control System Lectures. In this lecture, we will understand how do we find out gain margin and phase margin, and also understand the definition of gain margin and phase margin, and how do we find out using a polar plot. So, just a recap, a closed loop system is Cs upon Rs, Gs upon 1 plus Gshs, and the characteristic equation is 1 plus Gshs, and put S is equal to j omega in the open loop transfer function of this feedback system, we get Gj omega Hj omega. And it is gain margin, phase margin is about assessment of the relative stability, and we will also know what is phase crossover frequency and gain crossover frequency. Since the word margin itself relates to the relative stability of a system. So, now to understand what is a gain margin. So, here this is a imaginary axis and a real axis. In this we have drawn a unit circle. Unit circle means a circle having a radius 1 and centered at origin. Once we have drawn this unit radius circle and we have a polar plot, this is a polar plot. I have taken a polar plot, this is a polar plot, this value, this part is a polar plot. Now, we can see here that this polar plot intersects the negative real axis here, and the magnitude of the polar plot at phase angle equal to minus 180 degree, as written it is A. This is the phase angle which is measured from the positive real axis. So, that means the phase angle is minus 180 degree and the magnitude of Gj omega Hj omega at that point is A. Okay. So, this is the magnitude at angle equal to minus 180 degree. Now, for this A to be 1, that is 1 here is the margin where the system is marginally stable, that is limitedly stable. Now, for A to become 1, for this A to become 1, we have to multiply A into 1 by A, and this will result as 1. So, that means that this 1 by A is known as the gain margin. The product what we multiply to the value of magnitude when the phase angle is minus 180 degrees. So, we will understand here, if the gain of a system is increased by a factor 1 by A, then the magnitude Gj omega Hj omega becomes 1 if you multiply A into 1 by A. And what is A? A is the magnitude of Gj omega Hj omega when the phase angle is minus 180 degrees. So, gain margin is the factor by which the system gain can be increased to drive it to the verge of instability. Therefore, gain margin can be defined as the reciprocal of the gain at the frequency at which the phase angle becomes minus 90 degree, and the frequency at which the phase angle is minus 180 degree is called the phase crossover frequency. That is, at what frequency the phase angle is minus 180 degree of Gj omega Hj omega is known as the phase crossover frequency. This is the phase crossover frequency. So, as mentioned, gain margin is 1 by A, and A is the magnitude of Gj omega Hj omega, magnitude of Gj omega Hj omega when the phase angle is minus 180 degree. So, for example, if we get the value of A as minus 0.39, that means we use it as A, which will be 0.39. Therefore, the gain margin will be, the gain margin in that case will be 1 upon 0.39, and this A is obtained. We will find the frequency of the Gj omega Hj omega when phase angle is minus 180 degree, and then find out the magnitude A by substituting that value of frequency. And what is that value of frequency? Known as phase crossover frequency. And in decibels, as mentioned here, in decibels, gain margin is written as minus 20 log A, because log 1 by A 20 log 1 by A is taken as A raised to minus 1, that means 20 log 1 by A. So, this can be written as minus 20 log A, because 1 by A is nothing but A inverse. So, minus 20 log A is the gain margin in decibels, and since this point is 1, right, this circle is having a unit radius, that means the value of A for a stable system will always be less than 1, and if it is less than 1 means log A will be negative for a stable system. Log A is negative, and hence the gain margin will be positive, because this minus sign and the negative value of log A cancel out, and gain margin is positive for all stable systems. It means that if the gain margin is positive, the system is stable. So, gain margin can be written as 1 by A, and in decimals it is minus 20 log A dB. So, now we will look at what is the phase margin. Now, phase margin here is phase angle is measured from the negative real axis in the negative value, right. If the phase angle is, for example, minus 150 degree, if we get the phase angle, because when we write substitute S is equal to j omega and we get G j omega Hj omega, we get a magnitude and phase, and if the phase angle is minus 150 degree, means for example, this is minus 150 degree, we do not write it as minus, and that means right. So, this will be, that means it is in the clockwise direction here. This is 150 degree. If the phase angle is minus 150 degree, we mark it here as 150 degrees. Now, what is phase margin? Now, we can see that this is minus 180 degree, and if the phase angle becomes minus 180 degree, it means if the phase angle becomes minus 180 degree, like this. This is our unit radius circle, the phase angle is presently 150, and if the phase angle is less than 180, it will be somewhere here, this will be the phase angle, and now if the phase angle is 180 degree, this is a unit radius circle, that means this will be the vector. So, that means the phase angle is minus 180 degrees. So, we can see here that this is an additional margin which can be added, so that the system goes to the verge of instability. That means what we write, this is minus phi m. For example, we have minus phi m, which is equal to minus 180 degrees. So, this is an additional phase margin which is required to bring the system to the verge of instability, because when the phase angle is 180 degree, that is minus 180 degree here, it means that the polar plot like this, the polar plot is having a magnitude 1 as well as phase angle minus 180 degree. So, this is the where the system is limitedly stable. Beyond this, then the system will be unstable. So, now this is the additional phase lag. So, how do we define? The frequency at which Gj omega Hj omega is 1 is called the gain crossover frequency. Now, here this is a unit radius circle and this is a vector. This polar plot is crossing the unit radius circle at this point, and the frequency when the magnitude is 1, it means that the magnitude of Gj omega Hj omega is 1 and the frequency at that time is known as gain crossover frequency. It is given by the intersection of Gj omega plot and the unit radius circle, that is Gj omega plot, this is the plot, and the unit radius circle centered at origin. So, at this frequency the phase angle is equal to minus 180 degree plus phi m. So, this is the phase angle, right, this is the phase angle, and phase margin is always measured from the negative real axis. Its value is positive from the negative real axis. That means, this when you are measuring the phase angle, right, this phase angle, this phase margin is measured from negative real axis and it is measured as a positive value. If an additional phase lag phi m is introduced at the gain crossover frequency, this is what I mentioned, the phase angle will become minus 180 degree, whereas the magnitude remains unity. That means, already the magnitude will be at unity, it is understood, because when this phase angle is at minus 180 degree. The Gj omega plot will then pass through minus 1 plus j 0 point, driving the system to the verge of instability. So, this additional phase lag is known as the phase margin. So, the phase margin is this defined as the amount of additional phase lag at the gain crossover frequency required to bring the system to the verge of instability. Phase margin is measured positively in the counterclockwise direction, as mentioned here also. That means, the phase margin, if it is this, the phase margin is measured positively. If this value is 30 degree, that means phi m is 30 degree here, because we are measuring from here to here. The phase margin is always positive for a stable feedback system. So, that is what we have mentioned here. The phase margin is maximum till minus 180 degree. Now, for example, if the phase margin is here, how we are writing phase margin as? Phase margin is equal to the value of phase angle at the gain crossover frequency plus 180 degree. For example, this is written as 150 degree, that means minus 150 degree. So, phi m will be equal to minus 150 degree plus 180 degree. So, that comes out to be 30 degrees. So, this is the value of phase angle which is measured from the positive real axis in the negative direction. So, phi m will be minus 150 degree plus 180 degree, which is nothing but 30 degree. Now, in case the plot goes something like this, that means the phase margin is here. The phase margin will be here, whereas what is the phase angle? For example, this is 30 degrees. The phase angle will be 180, that is 210 degrees. So, in that case what will be the phase margin? It is, this is minus 210 degrees, that is minus 210 plus 180 degree, which will be nothing but minus 30 degree. That means, if it is now crossing that minus 180 degree axis, it means the phase margin becomes negative. So, for a stable system, the phase margin is always positive, measured from the negative real axis in the counterclockwise direction, in this direction, as I have shown the arrow here, it is measured in this direction, and the phase angle, if the phase margin is negative, it means the system is unstable. We can see here that this plot has crossed the minus 1 plus j 0 unit radius circle. So, already that means the system is unstable here. The gain margin here will be negative, because log A will be more than 1, and we have minus 20 log A. So, the gain margin in decibels will become negative. That means, for a stable system, both phase margin and gain margin should be positive, and if the gain margin is negative or if the phase margin is negative, then the system is unstable. And if the plot crosses the minus 1 j 0 line and the phase margin is minus 180 degree, that means the system is marginally stable. So, these are the steps to find the gain margin. Rationalize the given open loop transfer function, equate the imaginary part of g j omega h j omega to 0 and find omega, that omega is the phase crossover frequency. Find the magnitude at phase crossover frequency, and that magnitude is nothing but A. Gain margin is 1 by A and gain margin is minus 20 log A in decibels. An alternate method is, we can see that the gain phase, when the plot crosses the minus 180 degree axis, at that time the imaginary part is 0, it is having only a real value. So, the alternate method is, equate the phase angle of g j omega h j omega to minus 180 degree, find omega, and that omega is the phase crossover frequency, and then magnitude at the phase crossover frequency. Gain margin is 1 by A and gain margin is minus 20 log A in decibels. Then how to find the phase margin? Equate the magnitude of g j omega h j omega to 1 and then find omega, that omega is the gain crossover frequency. Find the angle at the gain crossover frequency, that angle is phi, that is the phase angle, that angle is the phase angle, this phi, and as I already explained, if this is minus 150 degree, then what will be, if for example phi here is minus 150 degree, then therefore phi m will be minus 150 degree plus 180 degree, which is 30 degree, that is a positive value which is measured from the negative real axis. It is positively measured. That is, this is just an exception. What we talked about the gain margin and phase margin, its importance to test or understand the relative stability of a system. Now, for example, we have a system type 1 system and a second order system. Type 1 system means there is a pole at origin and there is one more pole which is not at origin. For such a system, when you draw the polar plot will look something like this. As we have already seen this, omega is equal to 0 and this is omega is equal to infinity. Here we can see that the value of A, that is magnitude when the phase angle is minus 180 degree, will always be A will always be 0. How much ever you increase the value of gain, it will somewhere go like this, it will somewhere go like this, but never cross the real axis. It will never cross the real axis. That means the gain margin will be 1 upon A, that is infinite. Always in this case the gain margin will be infinite, and therefore, gain margin is not a measure to correctly understand the relative stability of system. In such case, we can look at the phase margin, like that what is the type 1 system, what we are discussing about is 1 upon S into 1 upon S t. For this kind of system, the gain margin will always be infinite irrespective of the value, because A will always be 0 when phase angle is minus 180 degrees. So, for a type 1 second order system, gain margin always remains fixed at infinite value, as the plot always reaches the real axis at origin, because magnitude is 0, while phase margin continuously reduces continuously with increasing system gain. In this case, phase margin is the correct measure of relative stability. So, just a summary of what we have understood about the phase margin and the gain margin. The measures of stability in terms of gain margin and phase margin are valid for open loop systems only, that is GSHS. This is a open loop transfer function or a forward path transfer function of a feedback system. A large gain margin or a large phase margin indicates very stable feedback system, but usually very sluggish. Means large gain margin means the plot is somewhere here. So, we have a something like this. So, there is a very large gain margin here, which is where the system can go to the verge of instability, and also the phase margin is very large, but such a system is very sluggish. So, a gain margin close to unity or a phase margin close to 0, that is phi m equal to almost equal to 0, corresponds to a highly oscillatory system, because a marginally stable system, the response of a marginally stable system is highly oscillatory. A reasonably good degree of relative stability is gain margin of about 6 dB or a phase margin of about 30 degree to 35 degree. This is a summary of what we studied about the gain margin and the phase margin. Thank you.